IoT Unplugged, where we talk to industry leaders, innovators, and major players in the Internet of Things, bringing you the best and latest insights. Tune in to learn more. In this episode, I speak with Rachel Johnson, Principal Product Manager at MathWorks, about smart factories and AI and engineering, as she highlights the ongoing process of improvement in smart factory development and AI-based algorithm anomaly detection. To Season 3 of IoT Unplugged. In this episode, I am joined by Rachel Johnson, Principal Product Manager at MathWorks. Rachel, thank you for being here.
Thanks so much. It's great to be here today.
So for the listeners who may or may not know of MathWorks, could you talk about your role and perhaps provide some background into the company?
Sure, thanks. So my name is Rachel Johnson. I'm the Principal Product Manager for Predictive Maintenance Toolbox at MathWorks. And MathWorks is the software company that makes MATLAB and Simulink. So essentially, we create software that helps engineers and scientists do their best work. So this is including model-based design, technical computing, and AI, which I'm here to talk about today. And I support a global team that supports different organizations that want to develop AI-driven predictive maintenance and anomaly detection solutions. So that's mostly what I do at MathWorks.
Great. Thank you for that, Rachel. And as you've alluded to just now, we are here to talk about AI and smart factories, which is, really a evolving, exciting area. But before we get into that, I just wanted to get your thoughts on what you think defines a smart factory.
Yeah, that's a great place to start. So I think it's sometimes not always clear whether a factory is smart or not. I think a lot of modern factories are really on this spectrum of what we would consider a smart factory, and they're really getting smarter all the time. So when we talk about a smart factory, we're talking about combining traditional physical manufacturing with these advanced digital technologies. So this includes technologies like AI, also IoT, cloud computing, right, advanced analytics. But really the whole goal here on this path to becoming a smart factory is to improve automation and improve efficiency over time.
And how do you see smart factories using IoT devices? Could you talk about some examples in this area?
Yeah, absolutely. So smart factories, or factories in general, right, who are on this path to becoming smarter, they really have a lot of sensors already. They have existing hardware that's collecting data from their equipment. And on this path to turning existing sensors into IoT devices, they're becoming smarter over time. So we're seeing our customers taking their existing hardware and trying to turn those into IoT devices. So I'll give you an example. Let's say you have a network of sensors on a fleet of pumps in a factory, right? And you have a lot of historical data that you've been collecting from these sensors over time, over the lifetime of these pumps. Now we want to actually bring these on and connect them so that we're collecting all of this data and using that data to train an AI algorithm in MATLAB to deploy in operations. So now the algorithm can be monitoring all of those data streams coming in from those pumps in real time. And now we're maybe detecting anomalies on that data coming in. We can then flag the data as either everything is normal or something is an anomaly, right? Something happening that's different. And this is leading us, I think, towards this path of predictive maintenance, which is all about preventing unexpected failures and really being able to investigate problems earlier. So if that AI algorithm is letting us know that something different is happening in the pump, engineers can then go investigate it before it becomes a problem.
Which I suspect saves a lot of money and time further down the line.
It's exactly right. So it's saving money, saving time. Ultimately, we're moving towards more efficient operations.
That's great. There was something you said that I want to pick up on, because you said a smart factory or factories that might be moving towards becoming smart. Do you think this is an ongoing process of improvement? Is there ever a complete smart factory?
That's a great question. Yeah, I think we don't know yet, right? Because as digital technologies are advancing, we're going to see more and more applications become available to on the factory floor, right? So now as AI is improving and we're living in this world of data, there's becoming more and more applications that can really make use of that data. And I think it's all really coming back to the data that's available.
It's I know I said it earlier, but it's an exciting time in sort of thinking of all the possibilities. You mentioned predictive maintenance being an advantage of integrating IoT devices and smart factories. Could you talk about some other advantages?
Yeah, and we just talked about cost savings, efficiency, right, and moving into those improvements over time. And I think the potential advantages, a lot of companies are just starting to see this. So actually, recently there was a survey of 86% of manufacturing executives have said that smart factories are going to drive competitiveness in the next 5 years. So they're really looking for ways to do this faster using their existing infrastructure and seeing those benefits. So we talked about predictive maintenance. This is the area that I focus on, but there's also opportunities in areas like quality control, process optimization, energy management, any application that's allowing for some form of automation to improve efficiency, cost, and safety as well. So AI is really going to enable these smart factories to do that at scale.
And AI will be a big topic for us to discuss. But just before we move on to that, I think sometimes when we talk about these technologies, there might be a tendency to center the conversation around the possibilities, which of course is important. But do you think there might be any challenges into integrating these technologies for smart factories?
Yeah, so my role at MathWorks is actually working with a lot of companies who are in the process of starting to do this, right? So I see a lot of challenges happening, and there's common patterns. And I've mentioned this earlier, right? We live in this world of data. And I think right now, most of the challenges are happening on the data side. There's, I would say, the issue of not having enough data or not having collected it in the right way is easily the biggest blocker that I see for companies on this path right now. But even if they have enough data, actually being able to understand what it means and how to define what anomalies look like or what the problem is that they're even trying to solve. So I think a lot of companies right now are in this area where they have a lot of data, they have a lot of potential questions they're trying to answer, and they're trying to really wrap their heads around how to scope this, right? Where should they be starting? So this is why we always recommend starting with a scoped project, like a scoped proof of concept, right? Get that initial win, pick that really specific problem that you're trying to solve, and then build up from there.
And am I right in thinking that when it comes to, and let's, for brevity's sake, let's relate this to predictive maintenance, which is the area you work in. Am I right in thinking that it also matters the length of time that you've been collecting data for in order to understand what might be an anomaly?
Yeah, that's absolutely right. So historical data tends to be very important for training these algorithms for either anomaly detection or there's some more predictive maintenance applications like identifying different types of faults, right? So one of the big challenges, I think, around anomaly detection, predictive maintenance in general, is having the right type of data that represents the anomalies you want to predict. So I'll give you an example. Let's say we have a pump that's just been operating normally, right? We don't want it to fail. We've been just performing regular maintenance on it throughout its entire lifespan. So we actually don't collect a lot of anomalous data. The vast, vast majority of the data is completely normal. So what happens is we have this large data set of normal operating data and not a whole lot of examples of what problems might look like, right? These anomalies. So we might not even know what we don't know. And this is where there are different types of approaches to AI, and I can talk more about this later, where if all we have is good data, there are still approaches we can use to identify potential problems.
So why don't we use that as the point to discuss AI? Just to start off our discussion, because it is such a vast area, how is it contributing to the development of smart factories?
So Right now, I think AI is at the core of where smart factories are headed. And part of the reason for that is it's impossible for engineers right now to monitor everything that's going on in a factory. Traditionally, what's happened in the past is there might be a dashboard showing all of the different data streams coming in, and expert engineers would be looking at that data and saying, oh, this is an insight. I understand what's happening here, or this doesn't look right. But as the data is getting bigger every day, right? We're living in this era of data. It's becoming impossible for engineers to do that. And there's also insights that they may not have known existed. So I think AI is letting engineers use that understanding of what's already going on to actually uncover different patterns that may exist in that data.
I think based on sort of what you've been speaking about so far, we're at a very early point in understanding how AI can help. I think there was a phrase used that I really liked is we don't know what we don't know. And I think that defines it quite nicely. So with all that said, sort of what roles do you anticipate AI will play in this production factory environment?
Right. So AI algorithms are going to be trained on massive amounts of data from thousands of sensors. And I think it's going to encourage engineers to consider, where should I put my sensors in a way that's going to most benefit these algorithms? We're already seeing folks starting to think about these questions, right? On the design side, where do I actually put IoT sensors on my equipment such that I can design an accurate AI algorithm to uncover the information that I need? So back to talking a little bit about anomaly detection, because I think this is really one of the first types of AI projects that we see folks moving into in this space, because it's a fairly general problem to ask, right? What might look different in my data? So that's really the question that anomaly detection is asking: is everything operating normally, or is something different happening? It's more or less the most basic question you could ask about data. So this could be a sensor, it could be a process or a component. But what this is enabling engineers to do when we have an AI algorithm helping identify these is they can now go in, investigate that potential issue more quickly, and take the right action faster. So in the future, this is moving into using this to maybe optimize a maintenance schedule, right? Improve overall process efficiency, or maybe even loop this back into some sort of proactive maintenance action where I can actually change how my factory is operating based on the result of that AI algorithm. So I think that's the future where we might eventually get to. But most places right now are really just on that path. And I think it's important also to mention, because this comes up every time I talk about AI and engineering, right? AI is not a replacement for the knowledge of engineers. It's really going to be a tool, and is acting right now as a tool for them to utilize their expertise better and really be able to scale what they're doing right now.
Is that a conversation you find yourself having? Like, this isn't something you need to fear. This is something that can help and support you in the future.
I think we see it a lot personally in the media, but I think most engineers are curious and starting to apply this, right? So most of the companies that we work with, they say, right, we see the value of AI and we're looking for ways to utilize it and to help it improve the efficiency of our operations.
Yeah, I do wonder when it comes to AI whether there's just an element of fear mongering about replacement, and just when a new and emerging technology comes, how to apply it appropriately, which is kind of the message that I'm getting from what you're saying here. It's also interesting to sort of hear from you how AI is meant to be a tool to help with some of the heavy lifting, but now lots of data is sort of becoming a challenge in and of itself. So could you talk about the process involved when you're designing and deploying an AI-based anomaly detection system? I imagine there's a lot of work that goes into that.
Sure. And I can talk through this, I think, 4 major parts, and we can stop and discuss each one along the path as you like. But It's really a process all the way from the beginning of planning and gathering data down through deployment and integration. So let me just start stepping through this, but no surprise based on what we've talked about so far, it always starts with the data. So step one really is about gathering data and defining the problem. And these go hand in hand, I think, because this means how do we understand the problem we're trying to solve and what data we even have to support that problem. If we want to detect a certain type of anomaly, but we don't even know what we're looking for, that might not be the problem that's worth solving at this point, right? So we need good data. We need a scoped problem to solve. There are a lot of companies who try to bite off too much. They say, I want to design predictive maintenance for my entire factory all at once. Unlikely to be successful right out of the gate. So starting with that scoped problem and then building from there, most engineers, they already have a really good understanding of how their systems operate. They know what the major problems are, right? What are the biggest drivers of failures and the what's causing the most problems in their factories right now. And so that expertise is really crucial in creating the right data and the right problem. So that's step one. And when we have decided on that, step two is really, okay, let's take this data and explore and pre-process it. So this includes organizing, labeling, pre-processing the data. The goal here is to get that data into a clean state so that we can use it to train an AI model. I'm going to talk about something called time series data, time series signal data here, because that's typically the vast majority of the type of data that our customers have. So we're talking about data over time from, say, vibration sensors or temperature or pressure sensors or current and voltage sensors. And this is different than, say, text data or image data. There's a slightly different approach we would take with those data types. But for signal data, we're typically talking about chunks of time where I can say, in this chunk of time, do I know that an anomaly happened, right? Can I label that? Can I say that, during this was weird and different, and during this was normal operation, right? So being able to separate that out is really helpful in designing a good AI model. But part of this process of analyzing data, processing data, also includes a step called feature engineering. And I think this is overlooked by a lot of AI folks, or they think it's not necessary. But what we find is this is extremely important for designing an accurate AI algorithm. And what feature engineering is, it means we're extracting relevant quantities from our data that can help us differentiate between normal and anomalous information. So as just maybe a very, very simple example, if we have a signal and maybe the mean value of that signal has shifted when anomalies occur. So that might be a useful type of feature to say, okay, let's look at the mean of the signal. Now, there's much more complicated features. There's many that are specific to the type of data that we're talking about. But this process is really important to feed into the AI models.
Right, and you said that it's something you think is overlooked. Why do you think it gets overlooked?
So in this world of deep learning, it's sometimes said that deep learning will do the feature engineering for you. And while that's technically true for some types of deep learning models, most deep learning models can still benefit from feature engineering, especially in the case where we may not have enough good data. Feature engineering becomes really important when we either don't have enough data, which is a common problem, or we don't have enough labeled data. So engineers tend to understand what features are important, and they can actually accelerate the process of getting to a good, reliable AI model more quickly.
Right, okay. And you mentioned there are two other steps, is that right?
Yeah, that's right. So we've gotten through, scoping our problem, exploring our data, pre-processing with feature engineering, and now we have some, good labeled process data. Hopefully, I would say those first two steps are about 80% of the work. But now we actually have to train the AI model and validate it. And this is actually going to be an iterative process with step 2. So we could be talking about with AI machine learning or deep learning models, but we need to train several possible models because we don't know which type is going to give us the best result. It's pretty unlikely that you will know just by looking at the data which type of AI model will be the best fit. So trying a whole bunch of different types and iterating to see how is the accuracy? Is it what I need? Do I need to go back and get more data? Are there different features I need to extract? So kind of iterating and going back and forth is really important. And because this is an iterative process, at MathWorks, we have created some interactive tools that help engineers do this more quickly. So there are tools like the Diagnostic Feature Designer, which is an app in Predictive Maintenance Toolbox, which is meant to help engineers experiment with different features. So they can import some data, extract and compare a bunch of useful features, and then use that to then go train a bunch of AI models and then come back and iterate, right? So doing that process very quickly is going to get you to a better result.
And do you think this element of experimenting with AI is important, particularly for engineers who might not be well versed in using it in the first place?
Yeah, absolutely. And I think you bring up a good point when you say that engineers may not be well versed in using AI, and I think we see that is true, but they are well versed in understanding how their equipment operates. And they understand the types of data that they're working with. So they really are experts on that, even if they might not be, say, have a PhD in data science, although some of them might. But we've essentially created products that are meant to help engineers do this work more quickly. So we have tools like the classification learner, which let you just go through and compare a whole bunch of different machine learning models and compare different accuracy, right? So you might not know specifically which algorithm will work the best or which features will work the best, but engineers are able to experiment and actually learn how to design these AI algorithms more quickly.
So what you're kind of saying is they've sort of got the skill set to be able to use these AI tools because they know what they're working with in terms of the equipment.
Yeah, that's right.
Okay, fabulous. And then what is the final point that you wanted to mention? We've got to AI training and validation.
Yeah, I didn't mention validation, so thanks for bringing that up. It's important to make sure that once we've trained an AI model, we actually validate it on new data that the model has not been trained on. Because if we're overfitting to the data that the model was trained on, then it's really good at making predictions on that data set. But once we actually show it something new, it might not be able to make a prediction on that. So we want to make sure that it's working just as well on some data set that we've never trained it on. So that's the validation piece here. But let's say we've gotten through all of that, right? We've trained an AI model. We're happy with the accuracy. We validated it. Now what, right? We don't just let it sit there. What do? Well, we're not going to get any value out of it unless we actually put it into operation. So this is the step 4, which is deploy and integrate. And this is where the requirements will be different depending on the company or organization that is using the AI model. So they might want to deploy that algorithm in a cloud environment where all of the IoT devices are streaming the data into the cloud, and that algorithm is now operating on streaming data. So that data is coming in, the algorithm's making a prediction, and then that prediction is being sent to some sort of a dashboard or an automated alert that's saying, there's an anomaly in, pump number 5. Okay, that's one type of deployment scenario. The other type, general category of deployment is embedded deployment. So there are cases where you may want to take some of your pre-processing and feature engineering algorithms and possibly the AI algorithm itself and deploy them directly onto the hardware at the edge. So this is right on the equipment itself, so that I can do some real-time processing. And I think which path you choose depends on what your overall requirements are and the timescales that you need to think about here. But ultimately, the idea is we're putting this algorithm, this trained, valuable AI algorithm, in operation so that new data from the equipment, I'm using this pump example, but it could be anything, right? New data is coming in, and we're using that AI algorithm to make a prediction that we can then use to then make decisions on the factory floor.
Great. Well, thank you for outlining that, Rachel. Earlier, you spoke about training models. Could you talk about how you decide the best AI learning technique for anomaly detection in particular?
Yeah, it's a great question. There's a lot of different techniques out there, and it's important to experiment with different training approaches, right, to find the best fit for the type of data, right? I'm coming back to data again throughout this conversation, but the best technique is going to depend on the type of data you have. So what this means is there are, I think, two major categories of AI that are going to relate to the type of data you have. So the first one is supervised techniques. This is where I have data that's labeled. I can separate it into normal and anomalous groups. Then I can use these supervised AI techniques. But many companies that we work with actually don't have that. They only have access to normal operating data. And that's because they're doing a lot of proactive maintenance, and these failures happen pretty rarely. Or sometimes they might have anomalies, but they haven't been saving the data, or it's integrated into all of their normal operation. So they don't really know where it is. So in this case, we can use unsupervised techniques. So there's supervised and unsupervised techniques. They're these major categories of AI algorithms, and they both include machine learning and deep learning. And it's really a variety of techniques to experiment with. I think it's never going to be completely obvious what technique will work best on what data set. So, right, engineers who understand the right features to extract, and then experimenting with different techniques is really the key.
Great. Well, thank you, Rachel, for an insightful discussion. I feel like I could probably talk to you about AI for hours, but it's been good to learn more, and a pleasure to speak with you today.
Thank you so much. Really appreciate you having me today.
IoT Unplugged.